Hey everybody, I'm going to do an example of using the central limit theorem in this video. So let's just jump right into it. We'll do some reminders along the way. So here's our situation. There's a small business. They use customer service surveys to keep track of their satisfaction of their customers. So the customers can rate the surveys 0, 1, 2, 3, or 4, with 0 being terrible and 4 being perfect service. And unfortunately for this business, the responses are uniformly distributed. So this is a discrete uniform distribution, which I haven't looked at in these videos, but all we need to know is that each of those 5 values, 0, 1, 2, 3, or 4, are equally likely to be given as a response. Okay, so if we did a histogram of responses, right, from 0, 1, 2, 3, and 4, what we'd expect is something like this, right? Similar to I've had the dice rolling show up in videos where we expect the digits 1 through 6 to all be equally distributed, right? So that's what our histogram would look like, something approximating this, because they're all equally likely. And then the question is, there's 2 questions. So the first one, what is the probability that a random customer will give a rating greater than 2? So let's start this by giving ourselves a random variable and then answering the question using it. So I'm going to take R to be the random variable, the customer rating, right? So a customer comes in, they give their rating, that's what the random variable takes on, the value of the rating, okay? Let's write out a little probability distribution table. Right, so we have the values 0, 1, 2, 3, and 4. Well, what are the probabilities? We can just use the fact that they're all equally likely and they have to add up to 1. So we're going to have 5 values that are the same that have to add up to 1. So each of them should be 1/5 or 0.20, right? So it's a simple enough computation. I'm going to throw in a couple of extra facts about the distribution, the discrete uniform distribution that we're going to need later. It turns out the mean of this distribution, so the mean of R, is going to be 2. I think that one's pretty evident, right? If we add up all these values, divided by how many we took, or if we took, you could compute the expected value pretty quickly of this thing, and you'll see that you get a value of 2. And this one's less easy to see, and I'm just going to give this computation. But we've seen a way to compute the standard deviation for a distribution. You take each of these values, subtract the mean from it, and square it, and then multiply it by its probability, and then add all those up. And that gives us our standard deviation. So it turns out here's the mean and the standard deviation for this variable. We don't really need those to answer this part though. So the question at hand is, what is the probability that if we ask a random customer to fill out the survey, that their answer is greater than 2? Well, we can pretty much read it off of this. I'm going to write it out a little more explicitly just to be clear. So we're saying, what is the probability? Being greater than 2 means that R equals 3 or R equals 4. We can use our addition rule. We don't have to subtract anything because these are mutually exclusive. The customer can only choose one rating, so there's no way to rate 3 and 4. And then each one is just 0.20. Okay, so we have a 40% chance of being greater than 2. Okay, now let's attack the second question. What is the probability that in a month of surveys, n equals 21, so this is our symbol just saying that means in this month they collected 121 surveys, what is the probability that this month will have a mean rating greater than 2? So here's where the central limit theorem comes in. So the big idea, remember, with the central limit theorem is that if we have a random variable, all right, so let's just do a quick, if I have a random variable of any distribution with a mean and a standard deviation, if I make a new variable called the sample mean distribution, meaning whatever data X is studying, X bar is studying sample means. If X is the weight of a random 5-year-old, X bar is the weight of the average weight of 10 5-year-olds, or whatever the sample size is. If X is the amount of liquid produced by a bottling machine per bottle, X bar is the average amount of liquid when you sample 50 bottles or whatever it is, right? So that's what we mean by the sample mean. And when we do this, what happens is, let's give these little subscripts. Mu of X bar, the mean of this new distribution, is exactly the same as the mean of the old distribution. And the standard deviation of the new distribution is equal to the standard deviation of the old distribution divided by the square root of the sample size, okay? Now, this really works best. We have a little rule of thumb. Either the original distribution was normal, or n is greater than or equal to 30. You can get away with it without these conditions, but you're always making an approximation, and the approximations can start to get a little bit, can get much worse when we get sample sizes smaller than 30, unless the original distribution is normal. Then we have no problems. So in this case, we don't have a normal distribution, but we are taking samples of a large size, n equals 121, right? So let's apply the central limit theorem. What it means is I've got a new random variable, r bar, and it is the mean customer rating for a sample size of 121. According to the central limit theorem, we can assume that r bar follows a normal distribution with the same mean as r, in this case 2, and a new standard deviation, which is the square root of 2. That's the old standard deviation, right? It's this old standard deviation. I'm just following this prescription over here. Oh, I forgot to write the last part, that this X bar follows a normal distribution with its own mean and standard deviation, and then these give what they are. So our standard deviation, remember, is the old standard deviation, or the original distribution standard deviation, divided by the square root of the sample size. So this is going to be the square root of 121. Okay, so let's compute this standard deviation. So let me get a calculator. Here we go. So I've got the square root of 2 divided by the square root of 121, and I'll round it to 3 decimal places, so 0.129. We'll put that in. Okay. Okay, so let's write this now with that in mind. So r bar follows a normal distribution with a mean of 2 and a standard deviation of 0.129. Okay, so we've taken this discrete uniform distribution and created a variable now that has a normal distribution, a normal continuous distribution. Okay, so let's now answer the question. The question is, what is the probability that a month of surveys will have a mean rating greater than 2? And my probability here is going to be, so it's the same thing except I've got r bar greater than 2. And for this one, since now I'm dealing with a normal distribution, I've got to defer to, I'm going to use a calculator again. So we're going to go here. And our mean was 2. Our standard deviation was 0.129. We're looking at, we want to know the probability of being above 2. And this is a fairly obvious answer once we see it, because 2 is our mean, right? Then the probability we're looking at is exactly half, because the mean is right in the middle that way, right? And we're sort of seeing a few things here. One of them is the difference between discrete and continuous. In the discrete case, when our mean was 2 and we set above it, we were jumping all the way to 3 or 4, because those are the only 2 things above it. With continuous, we could have an average of 2.1, right? So we can go just above 2. And so filling in all that area, we get a probability of 0.5. So let's go back to the whiteboard. And so this probability is 0.5. Okay, so that's our central limit theorem. We can start with any distribution, right? And we can change it, not exactly change it, but we can use it to create a new distribution, the distribution of sample means, which we'll have a lot of information about, right? This is an example where we knew the original distribution. When this is going to be most important to us is when we don't actually know the original distribution. Sometimes we might just know some information, like an estimate of the standard deviation or an estimate of the mean, but we don't know the distribution it follows. And then it's really important that we can take the samples, because we get a normal distribution, and then we have some information. Okay, that is it for this example. I will see you next time. Thanks, everybody.